we have learned about this dependent random choice lemma, which says that if this inequality holds, then you can find the subset of size at least something that every R vertices in there has at least this many common neighbors. And this is useful in proving upper bounds on the extremal number. So before we find the upper bound on the extremal number of complete bipartite graph, and we can extend that theorem into the following. So let S be an natural number. Let H be a bipartite graph. With vertex partition AB such that all vertices in B has degree at most S. Then what we can prove is there exists a C, a constant that depends on this H, such that the extremal number of H is at most this constant times n to the 2 minus 1 over S. So let's prove that. Let's say A is the size of the A, the number of vertices in capital A, and we let B be the number of vertices in B, and then M as A plus B. And then let's say D is 2 times C times n to the 1 minus 1 over S, which is the average degree of a graph with this many edges. Let's say C is bigger than 3 times MA. With this choice, suppose that we have a graph tree which is on n vertex graph with C times n to the 2 minus 1 over S edges. Hence, the average degree is bigger than D. Then what? We have to check the condition for the dependent random choice lemma. So we can compute this. So instead of T, we use S here, because what is the role of this F, which is the degree of the vertices in here. So based on our plan, we want to make sure that so S vertices, this R corresponds to S. So we want the S vertices on the set U to have a large common degree. And this was chosen accordingly. Then what's this? Based on our choice. If you plug this in here, this is bigger than 2S to C to the S. And this is lower bounded by n to the S divided by S factorial. And what do we know? M is here. Let's say here. Yeah, like but you have n to the s, and that's like cancels out. You have m to the s. So this is bounded by m to the s. But c is much bigger than m. So this is what? This is smaller than c to the s. So the final number is well over c to the s, which is at least a. Thus, dependent random choice lemma, this yields that there exists a set U of size at least A, such that, let's say exactly A, such that any S vertices in U has at least M common neighbors. So what we can do now, we take an arbitrary injective map pi from A to U, and let B be x1 to say xb. We embed these vertices x1 to xb one by one in order. Right before we embed fi, what we have that what common neighborhood of the image of the neighbors of this xi at size at least m, which is at least a plus b. Thus, there exists a vertex di in here, which is not an image of any vertices in either A or the previous vertex, x1 to xi minus 1. And we embed xi to pi, and by repeating this will never fail until we embed the last vertex xp. So we obtain an embedding of h into g. So this proves the theorem. And natural question is that how tight is this theorem? I mean, here we don't care about the multiplicative constant much, so we can ask whether this exponent is tight. But this is tight by the example of KST. And when t is large, we know that this extremal number is big omega of n to the 2 minus 1 over s. We know that when t is much larger than s to the s, say c to the s. That's the Book theorem. Okay, so this is this shows that the above theorem is tight. But what if we exclude this? Indeed, Colon and Lee conjecture that if H is KSS free, so if it doesn't contain KSS, then this might be little of n to the 2 minus 1 over s. I mean, they further conjecture that this is like smaller than some n to the 2 minus 1 over s minus epsilon for some epsilon, which is positive constant that depending on only h, not n. And what? For s equal 2, Gensler proved that the extremal number of the subdivision, one subdivision of AT is big O of n to the 3 over 2 minus 1 over 4t minus 6. So if we have no k to 2, so if you have h and one part its degree is n most 2 and no k to 2. So also one part degree is n most s. Then this is what? This is the subgraph of one subdivision of some complete graph, KT. It's not difficult to show this. So Gensler theorem confirms this conjecture when s is equal to 2. Just to add a note, use the probabilistic construction. It's not difficult to confirm that this extremal number is at least, say, this. So there is still a gap, but let me quickly check something. So that's the state, and for rider S, Sudakov and Tomon, Esteban Tomon, prove that the exponent number of n h is 3 of n to the 2 minus 1 over s. If again h is KSS3 and one part degree is n most s. So this shows that weaker form of this conjecture without actually making a polynomial improvement was not made, but it's showing that it's strictly smaller than this function. This function times some function that goes to 0. Okay, so that was one line of research. And here we consider the case that all the vertices on one part has degree m mod s. And such bipartite graph is S degenerate. You can take a vertex of degree s and then you can peel off repeatedly until you get nothing. And indeed, this degeneracy measures how sparse the graph H is. So if it has small degeneracy, then our intuition is that it's easier to embed it. And its extremal number might be small. Motivated from this, Erdős conjecture that this holds for all S degenerate bipartite graph H. So this is another famous conjecture. And best known partial result is by Alon Stiglitz, Sudakov, they show that it holds with the additional multiplicative constant 1/4 multiplied on this here. And using dependent random choice, we can prove the following weaker result. That H be an S degenerate bipartite graph. Then the extremal number of H is m mod n to the 2 minus 1 over 8s. So what can you do? So before, as long as you find one set U, where the most all of the R subsets have large common neighborhood, that was enough. Because in H, one part has bounded maximum, bounded degree. However, now all we know is that this is S degenerate, meaning that in here there could be one vertex with the degree at most S. Okay, but once you delete it, now it might be that all the vertices here has high degree and this has a smaller degree. And then you delete it, and you don't know where this high degree vertex are there. Where they are. So instead of that we need one set U, now we need two sets, U1 and U2, where the many sets, all the R sets all the S sets in U1 has a large neighborhood, and all the S sets in U2 also have a large neighborhood. So we can claim this. This G contains two subsets, U1 and U2, where every S, say, tuples, S subsets in UI has, say, at least n to the 0.1 common neighbors in U sub I minus 3. So the other one. So we can prove this using dependent random choice lemma twice. So apply dependent random choice with what? A being n to the 1 minus 1 over sorry. So n to the half, and t as so we have assume G has like n vertices, and then its average degree is at least this. Then let T be the average degree, and then let R be 3.5s, and then let T be 4s, and M be n to the 0.1. Then what? Again, with this choice, we can compute this. So this is the expression you get from the dependent random choice lemma. Then what do we have? So D is like twice times this. So if you do it, then this is 2 to the 4 to the S, and this to the 4 to the S is like n to the 4s minus half divided by n to the 4s minus 1. So this is like equal to n here. And this n to the 3.5s and 3.5s factorial. And what's m? M is this, so n to the negative 0.9 and multiply 4f, so which is 3.6 and okay. So let's say n is large enough. So let's say 1 over s and 1 over the number of vertices in H. So assume n is sufficiently large. Then what? This is, so this give you negative n to the, n to the minus 0.1s. As n is large, this is just very small number. And this is essentially, this is smaller than 1, so this is bigger than square root of n. So what does this yield? This yields a set u1 of charge n to the half, so square root of n, such that every 3.5 s subset of u1 has at least n to the 0.1 common neighbor. So now you have this u1. So here we have stronger property that every 3.5s vertex subset of u1 has large neighborhood instead of s. Then what our intention is that we will choose 2.5s vertices, and then we will take a common neighborhood of this as u2. Then what? You take this vertex set and this vertex set. Okay, it doesn't have to be this. Okay, you take this u1 and this u2, and what happens is that no matter how you take these s vertices, additional s vertices, some of these vertices might be chosen again. So one vertex chosen multiple times is okay. Then what happens? These s vertices together with this has large neighborhood in u2, and all of them are in u2 because common neighborhood of this is this. So common neighborhood of all of these are subset. That's still large. And if you forget this, then what you say is that this S vertices has large common neighborhood in U2 as we desire. So that's our plan. That's why we have chosen this number instead of S, which is this large number instead of S. So now what? We choose. So we kind of repeat the proof of the dependent random choice lemma. We choose vertices B1 to B2.5s uniformly at random. Okay, so one thing is that if S is not an even number, this is not an integer, then you might want to take a floor or ceiling to make it, work. Yeah, I will not worry about the parity for now. Then we choose this uniformly random. And then what we do, as we plan, we let U2 be the common neighborhood of these 2.5s vertices. Then what? The probability that this U2 contains a bad S subset. An S subset, which is bad, meaning that having at most n to the 0.1 common neighbors in U1 is at most we can compute this as right. So out of all choices or bad S of that, which is the most n choose S, the probability that they are included is what? If S subset has a common neighborhood of size at most 0.n to the 0.1, and then if B1 to BT are all, B1 to B 2.5S are all in here, then this S subsets are included in U2, which happens with the probability is to the 2.5S. But then what do you do? This is what? N to the S minus, say, 0.9 times 2.5 is like this, which is smaller than. Thus, what do we know? There exists choice of, say, this B1 to B 2.5S such that a subset of U2 has at least n to the 0.1 common neighbors in U1. Okay, so now as we explained before, we consider an arbitrary S subset S in U1. Then what? Now, I mean, this condition is okay when I is 2. And now we have to check whether it holds when I is 1. Then what? S union with this chosen B1 to B sub 2.5S. It has size almost 3.5S. So its set has at least n to the 0.1 common neighbors in G. But the definition of U2, all common neighbors, of this set lying U2. That's what? That's if F has at least, say, this many common neighbors in U2. And this proves the claim. And now we assume that n is large enough, n to the 0.1 is bigger than the size of H that we know. So with this claim, I mean, proving this is easy. So we have this, then from this G, you can find the U1 and U2. And then you have H with A and B, which is S degenerate. And then you just embed everything A here in U1. And then you embed one by one. It's just like what we did in the previous time. So yeah, I will not write down this part as this is easy. So this shows the power of this dependent random choice. Later in the lecture, we will see more application of this dependent random choice in finding larger structure. But here we have used it to find the small structure H in G, small subgraph. But we'll later see that it can be used to find the larger structure as well. Okay, so today we have learned about this dependent random choice, and then we use it to prove some upper bounds on the extremal number or bipartite graph, where two cases. One is that one part of this bipartite graph, all the vertices have bounded maximum degree, and two is where it is S degenerate. Okay, then thank you for listening. I will see you in next video.